Hello mathematicians, we're now going to extend our parametric approach to a look at the tangents and normals associated with our parabola. So we can see on our diagram here we've got a tangent at point P with parametric coordinates 2AP, AP squared, or with coordinates 2AP, AP squared. So when we go to find dy dx for our parabola, then we can now do it in terms of the parametric equations, x equals 2AP and y equals AP squared. So we saw this in the chapter on the derivative, where we can say that dy dx is dy dp over dx dp, so that treating them basically as fractions, these dp's effectively cancel out. So dy dp is, it's not 2AP, it's 2A, that P is gone, and, sorry, dy dp is 2AP, that 2 multiplied down out the front, and dx dp is 2A. So the 2A cancels out. What we're left with is that the slope of our tangent anywhere is P. So a nice general equation that the gradient of the tangent at any point is equal to the value of the parameter at that point. So again, think about it in words, just like that. The gradient of the tangent is equal to the value of the parameter. And it's just mathematically we write the tangent equals P, but it has a significance. So the parametric equation of the tangent is, so we're trying to get the equation of a straight line, so y minus y1 equals m outside of x minus x1, and you can see that if we multiply the p into the brackets or expand the brackets, we'll have px minus 2ap squared, and we'll bring the ap squared from the other side. So altogether, this is our equation for the tangent at the point where the parameter value is p. Now that's, again, easy to remember, relatively, and if you can remember it, fantastic, but it's the method that we need to understand. Once again, we don't have to memorize these equations. Now the gradient of the normal, following on again with skills that we already have. If the gradient of the tangent is p, then the gradient of the normal is minus the reciprocal of that, so minus 1 over p. Hence the parametric equation of the normal is y minus y1 equals m outside of x minus x1. The algebra is a little bit more fiddly this time. We have to multiply through both sides by p to get rid of the fraction, then rearrange, and we get this as the equation of our normal. Once again though, we don't need to memorize this equation. We just need to memorize the method. So now let's have a look at the case where we've got two tangents, and obviously the two tangents will intersect at a point. So the equations of the tangents at P and Q are, going on what we did above, y equals px minus ap squared for this tangent, and for the tangent that passes through point Q with coordinates 2aq squared, the equation of the tangent is y equals qx minus aq squared. So obviously this looks a little bit like the case of two equations with, forgetting the a for the moment, two unknowns, p and q. So if we set those two expressions for y equal to each other, that will be our method for getting the point of intersection of the two tangents down here. So when we do that, obviously p minus q outside of x equals a outside of p squared minus q squared. So that's just either setting them equal to each other and gathering terms, or you might like to think of it as subtracting one equation from the other Whichever way you think of it, I think you should do it to convince yourself that you know the process. And then obviously if we divide both sides by p minus q, the coordinate of x will be a outside of p plus q. And once we've got that as the coordinate of x, a outside of p plus q, plug that into either equation up above and we'll get apq as the y value. Again, it's probably really important that you convince yourself that you can do that algebra, but it's more important that you can do the process, and it's nothing new. What we can notice is that the tangents from the points at the ends of a focal chord intersect on the directrix. Now, where did I get that? Remember, we said if we have a chord joining these 2 points here, and if it passes through the focus, then PQ is -1. So that means that the y value of our point of intersection will be -a, which is exactly on the directrix, y equals -a. So, question 3. So it says find the equation of the tangent to this parabola at the point where t equals p. So we're talking about a parabola, a point P, this parabola, because it's 2at squared, has its vertex at the origin. We've got a point here where the value of the parameter is p. So the coordinates of this point will be 2ap squared. Now, because it said find the equation rather than simply what is the equation, you should probably go through the derivation, although it's a little bit fuzzy, but we need to remember this process anyhow. So remember, we want the slope of the tangent, which is dy dx, which will be dy dt in this case over dx dt. dy dt means that we differentiate this and we get 2at. dy dx, we differentiate this and we get 2a. 2a cancels out, and as expected, the slope of the curve, and therefore the tangent, at this point, or at any point, sorry, is equal to the value of the parameter. And in this case, the value of the parameter at the point we're interested in is p. So therefore, the gradient of the tangent is p. And so we put that into y minus y1, m outside of x minus x1. Expand our right hand side out, so that's px minus 2ap squared, and therefore y equals px minus a p squared. Part B, find the coordinates of the points where the tangent intersects the coordinate axes. So make sure that we're reading the question carefully. We want this point and this point. So cut the x-axis when y equals 0, which means that we want that will happen when px equals ap squared. So one of these p's will cancel, so when x equals ap. So this point here is going to be the point ap0, and we'll cut the y-axis when x equals 0, which implies that y equals minus ap squared. So this point is 0 minus ap squared. So nothing beyond what we could have done ages ago here. It's just in a different setting, which we're going to find is so often the case in maths. Part C, find the area of the triangle formed by the two intercepts in the origin. Okay, so now it's straightforward. That's a right angle triangle. Area of the triangle is half base times height. Doesn't matter which one you think of as the base and which one is the height. So it's a half of, let's take this as the base, AP, times the height. So the magnitude of that height is AP squared. We don't put the negative in, it's just how far is it. So our answer is going to be a squared p cubed on 2, and that's the area of the triangle. So again, think about what it is that you really need to understand, and is there anything that you need to commit to memory, and maybe jot down a little summary and then have a go at 9F and realize whatever the question asks, it can only be done with the tools that you've looked at.